Hello, students. Welcome back. And we have discussed last time with you the cyclic structure of the glucose, and we have shown you that there is a certain behavior, certain reactions, certain chemical reactions which are not shown by the glucose, but which are typical of the carbonyl compounds.
Yes, sir.
How many reactions we told you which were not shown by the glucose? This is an important question, students. This is an important question which I am telling you for the exam. The important question is that why why the cyclic structure of glucose was proposed, student, or what is the evidence that glucose has a cyclic structure, students? The important thing we told you, glucose, when we have written the Fisher projection formula for the glucose, that is called open chain structure of glucose. What I told you, the open chain structure of glucose was given, student. Where is the open chain? You can see that this is our open chain structure of the glucose. It contains one CHO group and 5 OH group and one primary. You can see one of the OH group is primary here, primary alcoholic group. This is called open chain structure of glucose. Now, as in the open chain structure of glucose, you can see, students, there is a free, what is there? Free CH double bond O group is present. This group is present, as you can see in this open chain structure. Is it present or not, students?
Yes, sir. There.
Open chain structure contains, therefore, we expect the reactions of the CHO group. And we have learned that CHO groups, they form sodium bisulfite product. Student, they react with DNP, they give DNP test, then they will form cyanohydrin reactions. All this we already learned. And for example, the following reactions cannot be explained by the open chain structure. Despite having aldehyde group, it does not give Schiff's test. It does not give sodium bisulfite. The pentacetate of glucose does not react with hydroxylamine, student. These are the important things, and is a question is on the paper.
Yes, sir.
Question is, which reactions are not explained by the open chain structure of glucose? This is a question in the paper which was given. Explain the reactions which are not given by glucose, open chain structure of glucose. Open chain structure of glucose, students. Can you tell me fast which reactions I have told you? Fast, student, 30 seconds. Name the reactions which are not given by the glucose. Which are the reactions we just told you?
Sir, telling. Sir, Schiff's test.
Okay. Does not give.
Sir, SCHIFFS test.
NaHSO3 bisulfite. No addition.
Yes, sir.
No product. What else?
Yes, sir.
Pentacetate of glucose does not form.
Sir, DNP test 2,4-DNP.
It does not give. Therefore, these reactions, this chemical behavior cannot be explained by the open chain structure of the glucose. It was proposed and it was considered that since glucose has got OH groups, as you can see, how many OH groups? 1, 2, 3, 4, 5 OH groups. And we know that carbonyl compound, students, when they react with alcohols, this is my alcohols, what happens? They will form, you know what they call as hemiacetal. Aldehydes will form hemiacetal if it is an aldehyde. If it is a ketone, they will form hemiketal. So there is a formation of hemiacetal and hemiketal. Are you aware of this reaction which we told you in the case of the carbonyl compound students? In the case of aldehydes and ketones, the reaction of aldehyde and ketones with alcohols. Therefore, it was proposed that since there are OH groups, the OH group may attack this carbonyl of the aldehyde of glucose and form what we call as a hemiacetal, and that is the true thing. There was verified experimentally also. Actually, we have shown the ring structure of glucose. Then after this, this led to the cyclic structure of glucose. What type of cyclic structure? This is a hemiacetal formation, as we have said here. What I am trying to say, देखो, this is my carbon 1, 2, 3, 4 and fifth carbon. We are saying the fifth carbon will enter into student a ring formation with the carbonyl of the glucose. This CHO group and this fifth OH group student, they are going to form a cyclic ring, as you can see here. And this carbonyl, the CH double bond O group students, you have CH double bond O group. If you see student, this group is sp2 hybridized. It is sp2 hybridized carbon.
Yes, sir.
And when it will form hemiacetal student, hemiacetal, the OH group will react with the carbonyl of the aldehyde group, like the acetal which we have shown here. Now in this case, a cyclic ring is being formed. A cyclic ring is being formed, as you can see that. And the result of this will be, student, this carbon number 1, the carbon number 1 of glucose students will become, from sp3 to you are going to sp2 to you are going to sp3 hybridization. This carbon number 1 now, carbon 1, this is my carbon 1 student, you can see it becomes sp3 hybridized, and this carbon is chiral carbon now. What is this? Chiral carbon now. Important point. What
Yes,
is a
sir.
chiral carbon? What is a chiral carbon, student? That stereoisomers which are optically active. It has an asymmetric carbon, students. It has an asymmetric carbon. You can see that from sp2 to sp3 hybridization. So this carbon is asymmetric, student. You can see that it is attached to 4 different groups. This is attached to 4 different group, students, and 2 possible configurations arise in this case: OH on the right side or OH on the left side. So there is, what is that? This are two forms of the glucose, because it was found that glucose exists in 2 forms, students. One is alpha, other is beta. Both of them have different melting point, students. So what happens? Now 2 possible isomers are there. You can see 2 possible isomers. When OH group is on the right hand side, this is my alpha D plus glucose. OH group on the left side is, student, beta D plus glucose.
Sir, your voice is breaking right now.
Voice is breaking. There are 2 forms of the glucose: OH group on the right side and OH group on the left side. You can see when OH group is on the right side, we call alpha D plus glucose. OH group on the left side is called beta D plus glucose. So students, can you listen my sound? Can you listen me? Or any problem?
Sir, your voice is breaking right now.
Breaking network.
Sir, breaking. Your sound is breaking.
Sound is breaking. Okay. I'm checking my network.
Yes, sir.
Network sound is breaking. Network is okay. The speed. Let me test the speed of this. Check out. It will come again. आवाज आ रही है? Is the sound coming? Is the sound coming? Can you listen me?
Sir, you can try switching off your video once.
अच्छा आवाज आ रही है कि नहीं अब?
हाँ सर, आ रही है आवाज, आ रही है, अब आ रही है अब।
ओके, ठीक है. All right. So students, what I am trying to explain to you that what we are seeing here, that at carbon number 1 where the CHO group is present, student, we can see the OH group can be on the right side or OH group can be on the left hand side, students. When the OH group is on the right hand side, that is called alpha D plus glucose, and when the OH group is left hand side, that is called beta D plus glucose. So these two forms of the glucose, alpha D plus glucose and beta D plus glucose, they differ at C1 configuration, student. What is the difference? They are only differing at C1 configuration where the OH is on the right and on other C1 OH is on the left. And these are called anomers, student. Question has been asked, what are anomers? They are called anomers, student. What I'm saying? What are anomers? In the aldohexose, glucose is a aldohexose. When hemiacetal is being formed, at the carbon at which hemiacetal is formed, student, there is a difference in the configuration. OH group is on the right side, that is alpha. OH group on the left side, that is beta form. So there is a difference between the two, and we can say that alpha D plus glucose and beta D plus glucose are anomers. Here I have again explained to it because this question was given. These two isomers differ in the configuration of the hydroxyl group at C1. So such stereoisomer that differ in the configuration at C1 are known as anomers, student. They are known as anomers. Therefore, alpha D glucose and beta D glucose, what type of stereoisomers they are, student? They are anomers. They differ at the configuration of OH group at C1 position. At C1 position. Now the Haworth proposed a structure for the glucose, just like Fischer has given open chain structure. The cyclic structure is better written by the Haworth because he used, it is also called glucopyranose. Why? Because organic compound, we know a pyran. Pyran is a 6-membered ring. This is a pyran structure. Pyran is, student, 6-membered ring. Therefore, in the pyran, you can see oxygen is there and this is 6-membered. Therefore, they suggested that Haworth said that we can draw the glucose structure. There are two glucose. One is alpha, other is beta form of the glucose. So what we do, this you can see is 6-membered ring with the oxygen, which is our pyron type of ring, pyron ring. Those groups which are on the right side, they have been written lower side and others on the upper side. So by this way, the carbon 1, 2, 3, 4, 5, 6 carbons are there. So this is our alpha form. In alpha form, the OH group is located, you can see downward. In the beta, everything is same except this one C1. At C1, OH group is on the top, hydrogen is in the lower case. These two are called anomers. Student, they are examples of anomers. So alpha D glucopy, that is why the name is written like alpha D plus glucopyranose. Because pyran is a ring from which we have used this six member, pyranose. Alpha D plus glucopyranose and beta D plus glucopyranose. Student, this is a Haworth representation, Haworth structure of the glucose. We told you how to be able to write the Haworth structure because it was given in a question. Question was draw the Haworth draw the Haworth structure of alpha D plus glucopyranose.
Yes, sir.
The structure of this. How do we do? This is our open chain structure, which I told you to remember open chain. I am using a short trick. This is my glucose. This is my CHO. And student, the group on the right side is OH. The group on the left side is OH students. This is OH students. Then I write OH. Then the ones, this is hydrogen, then this is hydrogen, hydrogen, and the last one you know is CH2OH. So this becomes the Fischer projection of the glucose. If I have to write this, is easier way to write the Fischer projection of the glucose. Now we have to see that this is my carbon 1 and this is the carbon 5. This is where the hemiacetal formation will take place. At which carbons? Question are put like this: at which carbon hemiacetal formation will take place? Carbon 1 and carbon 5 students.
Yes, sir.
C1 and C5 are involved in formation of hemiacetal. I'm again using hemiacetal because this is important. So cyclic ring is formed. So what we did here, that we now CHO number 1, number 2, number 3, number 4, number 5, number 6. We have written it in a cyclic form. Now this OH is going to attack here student, and this H goes there. So what we get student. So this is a simple way to write it. In one case OH will be on the top, other case OH will be left. Those groups which were on the right side I have written lowercase, and those which are on the left hand side they are written on the top. So by this way, I create two forms of glucose, as you can see. One OH group lower, other OH group upper. Okay? These are the two forms of the glucose, alpha form and beta form. So in alpha, OH is lowercase. In beta, OH is on top. See the difference? This was the structure to be written in the paper. So this is my carbon 1, 2, 3, 4, 5, 6. 6 carbon. This is the way to learn the structures of the glucose. What is the relationship between the two structures? Tell me what is the relationship between two structures. One is called alpha D plus glucopyranose, and the second is called beta D plus glucopyranose. These two are related with the only difference is C1.
Sir, you can try switching off a video. I think that will.
It will stable, don't worry. Board is visible. Board, what we are writing on the board is visible.
Yes, sir. Yes, sir. Sir, board is clear.
Okay.
Yes, sir. Yes, sir. Yes, sir. Clear, sir. Very clear.
So no problem. You will get a recorded video also after this. So alpha D plus glucopyranose and beta D plus,
yes,
they are examples of anomers. The recorded video will be sent to you. Don't worry. If any doubt is there. Now these are important questions in the paper. Draw the Haworth structure. You can draw the Haworth structure by this trick. This is a way to simplify student, and this is a chair form of this.
Okay, thank you, sir.
Is not required for our course. We have only shown it There are two positions, axial and equatorial. Axial and equatorial. Now we are coming to the second compound, which is fructose. Fructose, student. Fructose, students, have the same molecular formula as the glucose, C6H12O6. And after the reactions were performed, students, just as in glucose, to establish the structure of glucose, certain chemical reactions were performed. In fructose also, the chemical reactions were done. We are not giving those chemical reactions. They are not been given in your course, but if you want, you can study them. This is not required. So our main topic is glucose and less for the fructose for this our course. Chemical reactions proved that fructose has got ketonic group. It is a ketone. It is not an aldehyde, students. Fructose reactions proved it is a ketone. You know, there are tests to distinguish aldehyde and ketones. It was found it is a ketone, student, and it was found to have 1, 2, 3, 4, 5 OH groups. 5 OH groups were present. And the structure of fructose is written before you. This is the structure, open chain structure of fructose. Open chain structure of fructose.
Yes, sir.
This is a ketonic group is at number 2 position. You can see it was found that carbonyl group is present at number 2 position. This is my carbon 2, 3, 4, 5 and 6 carbons. So when we write, students, when we write fructose, so what you have to do? You have CH2OH. At number 2, you have a ketone. 1, 2, 3, 4 balanced. Then the configuration or position of the OH. Third, this is my 1, 2, third carbon. This is asymmetric carbon. This is asymmetric carbon now. The OH is on the left side, as you can see. Then what do we have, students? Then you have, this is our carbon OH and this is our H. So in this case, what do you find? OH group on the right hand side, OH group on the right hand side, H on the left side. This is the CH2OH. So you can see that there is a primary. This is example of the primary alcoholic group. This is also a primary alcoholic group. There are two primary alcoholic group, one ketone group. And further, it was found that there is it also exists in cyclic form. Cyclic form of fructose. Just as there is a cyclic form of glucose, there is a cyclic form of fructose, students. How will we write the cyclic form of fructose and where it will be formed? You will see that in this case, CO group is present at position 2. This is my CO group. Where is my CO group, student? This is the at position 2, CO group. And 1, 2, 3, 4, 5. This is my 5th carbon. This OH, students, will form a cyclic ring with the carbon 2. Which one? 5th OH group and 2nd CO group. They will form a cyclic ring, student, which we call as, there will be a cyclic hemiketal. It is a hemiketal because it is formed by the ketone. As we have seen, the carbonyl groups react with alcohols. Carbonyl group react with alcohols to form acetals. So here carbonyl groups are reacting with ketone to form ketal. This is again, this will become now a 5-membered ring, student. This will become a 5-membered ring. Because it is not carbon 1, it is carbon 2. Can you tell me? It is not carbon 1, it is
Yes,
found
sir.
between
Calculate.
carbon 2 students. This
Yes, sir.
carbon. So what will happen? There will be OH group here, then CH2 group here, then the carbon 2 students at carbon 2, what is happening? There are two possibilities now. OH group, you can see OH group on the right side or OH group on the left side. Now there are two types of structures which are possible, student, at carbon 2 I'm saying. At carbon 2, two structures are possible, OH group on the right side or OH group on the left side. Can you see that? Five-membered ring. This is a five-membered ring, students, in the case of the fructose. So there are two forms of the fructose. Fructose is again was found to belong to D series. Fructose belongs to D series, students. What is the meaning of D series, students?
Hmm.
The lowest asymmetric carbon OH group is on the right side, which is the lowest, that fifth one. Fifth one is used here, then the next one. In the open form, in the open structure, you can see that the fifth OH group is the one, student, which is the lowest asymmetric carbon. This, when this is on the right hand side, that is called D. So the fructose was also found to be D fructose. It is written as D fructose, D fructofuranose, D. So it is also belonging to D category. That means this OH group is on the right side. That is the D fructose. And in the case of glucose, it was found to be dextro. D-glucose was found to be dextrorotatory. This
I'm also
fructose
looking
was
there.
found to be levorotatory. So there is a negative minus sign which is written. You can see minus. What we are writing, D minus fructose. See the difference? This is now the cyclic structure of the fructose, student. It five-membered ring is a furan in organic chemistry. In our organic chemistry, five-membered ring with one oxygen is furan. The structure of which I have shown here. This is my furan. What is the structure of furan? Furan is a five-membered ring. This this is furan.
Yes, sir.
So the cyclic structure of the glucose has been written like beta D minus fructofuranose and beta D minus alpha D, alpha that, in which at C2, now the configuration difference is at C2, where the OH group is different in the fructose, student, at C2 position. In glucose, but where was the difference? At C1 position, because aldehyde was present at number 1 carbon, ketonic group is present at number 2. So here OH will be generated. So another stereo center will be generated at position 2, student, one OH on the right, one OH on the left. So there will be two isomers of fructose also. One will be alpha D fructose and other will be beta D minus fructofuranose. Why furanose? Because furan is a five-membered ring and glucose and fructose is forming a five-membered ring ketal, student. This is a ketal. And this is a Haworth form of the same, which we wrote for glucose also. Most likely the questions are going to be asked on glucose in our exam, students. Less information is given in the books in our course for the fructose. But we should know the cyclic form of fructose, and the Haworth structure of the fructose is written in the same way as we wrote for the glucose. See, this is the Haworth structure. I will write a furan ring. This is a furan ring, student. Now
Yes,
here
sir.
the carbon 1 is my CH2OH group because the ring is five-membered. So here OH group is on the left side. It is written All those groups which are on the left, student, they will be written on the lower case, and the ones which are on the right will be written on the higher case. So in this case, student, what we are writing? CH2OH uppercase, OH lowercase, add position 2. Add position 2, student. And then what you have? OH on the left, OH on the left, that goes up. OH on the right goes down. Groups on the left goes up. So like this, students, we are able to write the cyclic structures of fructose. What is the relationship between these two cyclic structures of fructose, student? They differ at which position? At what position the configuration is different in fructose? At position C2. So these are two anomers. They are anomers of fructose. Question has been asked, what are anomers? That's why I'm spending more time on this. You can note down this, students. Where is the cyclic ring formation? At carbon number 2 and carbon 5 OH group is involved in cyclic hemiketal formation. What do we call this as? Cyclic
Yes, sir.
hemiketal formation. And it is clear now, students? I've
Yes,
drawn.
sir. Yes, sir. Clear, sir.
Okay. You can note down, and we will give you the videos also, which you can see. Most likely, our main attempt is glucose, but whatever in the course is written, we are doing it. We don't need much more than this for the fructose. So there are two alpha and beta fructose also. Both of them are anomer, students. You have noted. I will proceed further.
Copy the 2 minutes. For 2 minutes.
Okay, copy everything. Important, important, important. Any question can be asked in the paper.
Yes, copied, sir.
Okay. देखो, some questions which have been asked in the paper, again I am writing for you, which may not be available in the books. This question is important. What are anomers? Was given in the paper. And we have already explained you in the case of glucose. Add carbon 1 configuration. One OH group on the right side is called alpha D plus glucopyranose. And the one OH group on the left hand side is called beta D plus glucopyranose. These
Yes,
two
sir.
are anomers. Why? They differ at which configuration? C1 configuration.
Okay.
At C1, what happened? Hemiacetal formation took place. Right or wrong? Tell me. So at
Right, sir. Right, sir.
in the case of glucose, what happened? There is a hemiacetal. Which carbon of OH group was involved? Carbon 5. What we said to you, what we proposed to you. For example, here you see this is my D plus glucose. This is my D plus glucose. Okay? This is the open chain of D plus glucose. Because what will happen? The glucose will have open as well as cyclic forms when you will put it in water. But maximum will be cyclic form, but some open form is also there. The equilibrium is existing. Equilibrium is there. The
Yes, sir.
open form you can see at carbon 1 and carbon 5. These are the ones, student, which will be involved in hemiacetal formation. And this is the process which we showed. This is the 6-membered ring. And 5 OH will be the one which will attack this and form a bond. So what happens if it bonds with this carbon, students? This becomes OH. Now the OH can be lower or upper. This gives rise to This gives rise to student two structures. One is alpha D glucopyranose, other is beta D, and they are nothing but anomers. So glucose is both an aldehyde at C1 and alcohol at C5. These two groups can react with each other. So in glucose, there are both two groups present. Okay? Why? What I'm saying, in glucose, both CHO group and OH are present. Both these groups are present. And C1 and C5, these two groups react to form cyclic hemiacetal. What we call this as cyclic hemiacetal, or give glucopyranose. Why the name was pyranose? Because pyranose is a six-membered ring. We have shown you. Pyran ring we have shown you is a six-membered ring. What is pyran ring? In organic chemistry, student, this is pyran. It is a six-membered ring, but one oxygen is there. Here, one oxygen is there. Same. So when we will write the structure, there will be two forms of the glucose now. One in one case OH up, in other case OH down. This is what we call as anomers. They are called as anomers. And this carbon one has become chiral, student, now because it has become asymmetric carbon. Therefore, an anomer is an epimer at the hemiacetal or hemiketal carbon in a cyclic saccharide. Saccharide means those sugars which we are talking about. So we can write the answer of what is anomer. Anomers are stereoisomers of cyclic sugars that differ in the configuration only at the hemiacetal or hemiketal carbon. Another example.
Yes, sir.
Fructose is both a ketone at C2 and alcohol at C5. So what will happen? The OH group of 5 will form a hemiketal at C2 position with C2 carbon. These two groups can react with each other to form cyclic hemiketal. So what we will get? Fructofuransoe. Why we call it furanose? Because furan is this is a 5-membered ring, student. Fructose we have 5-membered ring. Glucose we have 6-membered ring. Because ketone group is present at number 2 position. So when fifth OH group will react, what will be the size of the ring? 5-membered. And you know, 5 or 6-membered rings are quite stable.
Yes, sir.
And the lower rings will not be stable, student. They will not exist. There will be a lot of angle strain. That is why mostly 6-membered rings are formed. Or after that, 5-membered rings are formed. Because in glucose, you will learn later that a 5-membered ring also exists for glucose. It also forms 5-membered ring. So fructose forms two types of fructose. One is called fructofuranose. There are two fructofuranose, students, which we have shown you. One is alpha D minus fructofuranose and other is beta D minus fructofuranose. These are two anomers. They are also anomer, student, and they differ in OH configuration at C2 carbon, in the case of fructose. Whereas in the case of glucose, they differ in OH configuration at C1 carbon. So you have noted down, we will proceed further.
Yes, sir. Yes, sir.
This is a hemiketal formation. What is formed, student? Here hemiketal, and it has become chiral. Hemiketal formation. Another question which is asked many times is what is an epimer, and give an example. Just now I told you anomers are stereoisomers and they differ at the configuration of that carbon where hemiacetal or hemiketal is formed. In the case of glucose, we gave you example alpha D plus glucopyranose and beta D plus glucopyranose are anomers. They differ at configuration C1 of OH. Okay? In alpha, OH on the right side, in beta, OH at the left side. That is the difference. We have drawn the Haworth structure also to show you that difference. Now, epimers are those stereoisomers which are differing in its configuration at only one chiral carbon atom and are called epimers. देखो, if at any carbon which is chiral, ठीक है, they differ in the configuration, they will be called epimers. In glucose, you know, when I say this is the glucose,
Yes, sir.
if I write this as a glucose student, how do I write glucose? Now we should have practice to write this open chain structure. 1, 2, 3, 4, 5 students, 6. Carbon, at carbon 2, the OH group was written on the right side. At carbon 3, it was written on the left side. Here right, here right. This is glucose. And I write hydrogen, hydrogen, hydrogen. This is my D glucose. Okay? And when I will write alpha or beta, then I will use Haworth structure. Haworth structure, students, you have seen Haworth structure, where we said alpha D glucopyranose and beta D glucopyranose. They were anomers. They were anomers. This is my. Now I can have some other compound, student, in which there is a change in position of OH. If supposing the OH position is different at number 2, 3, or at any carbon. If OH position
Yes, sir.
becomes different at any carbon, then what happens? They are called epimers. They are called epimers. For example, stereoisomers which are differing in its configuration at only one chiral carbon. This atom is chiral, this is chiral carbon, this is chiral. So any of the chiral carbon, if OH group position changes, then it will become epimer. And the two important epimer of glucose we have shown. This is D-glucose. This is D-galactose, student. D-galactose. This is an epimer of student D-glucose. And therefore, at which carbon it differs? देखो, carbon 4. See the carbon 4. This is carbon 4. See the carbon 4. OH on the right, here OH on the left. Can you see that? At carbon,
Yes, sir.
galactose has OH group on the left. Glucose has OH on the right at carbon 4. Can you see it? Tell me. Can you see the change in position of OH group?
Yes, sir.
So this is galactose. Galactose is an epimer of glucose, D-glucose. Another is D-mannose. In biology, you must be learning more than chemistry. In bio, did you learn about galactose and mannose?
Yes, sir. Yes, sir.
They are carbohydrates, they are sugar families, saccharides. What is the relationship between galactose and glucose? They are epimers. What is the relation between glucose and D-mannose? If I have to write a structure of D-mannose, first I will write glucose, then I will change the OH position at C2 position, add C2 position. See that C2 position? Where is C2 position? This one. Can you see C2 position? This C2.
Yes, sir. Yes, sir.
OH on the right, OH on the left. So D-mannose is nothing but a epimer of glucose. D-mannose is nothing but an epimer of D-glucose. Epimer means it will differ at the one of the chiral center carbon configuration, and the difference is at C2 carbon here. Here the difference is at C4 carbon. Now I've started giving numbers to carbon because this is important in biochemistry. Because at different carbon,
Yes, sir.
position will change. They are stereoisomers, student. They are stereoisomers. And we told you for glucose, there are how many large glucose has got how many chiral center? 1, 2, 3, 4. If n equal to 4, then 2 power n means how much? 4 to 8, 16 stereoisomers are there. Glucose has 16 stereoisomers,
Yes, sir.
and therefore these are stereoisomers. D-mannose and D-galactose are epimers of glucose, students, and alpha
Yes,
D
sir.
plus glucose and beta D plus glucose are student anomers. And anomers are also epimers, but epimers are not anomers. See the difference? Some questions are nowadays
Yes, sir.
framed for the 12th case like this, whether it is assertion is correct or not correct, students. So we can say that what we studied, student, important point. Anomers, I told you what are anomers. First, anomers I told you. Second, what I told you, student, what are epimers. The anomers are also epimers because they differ at one of the chiral carbon configuration. But in D-glucose, the anomers are at which position? Carbon 1. In fructose, student, D-fructose, the anomers are at which carbon? In fructose, at carbon 2. At carbon 2. Clear? Tell me with example, everything is clear?
Okay,
So
sir.
we know what are anomers, what are epimers. Okay. Another important thing which what is mutarotation? What is mutarotation? As I said that optical active compounds, students, optically active compounds rotate the plane of polarized light. So they have a rotation. They can be dextro or levo. Dextro will rotate towards clockwise and levo compounds will rotate towards anti-clockwise rotation. And we have said that glucose has two forms. How much glucose exists in two forms? You have alpha D glucose and you have beta D glucose. It is found the specific rotation of the two are different. Students, specific rotation of the two are different. One you are saying alpha D plus glucose. Other you are saying you have beta D plus glucose or glucopyranose. It is found that this has a specific rotation of 112 degree and this has a specific rotation of students plus 19 degree. So there is a specific rotation of the two are different. What happens when you put alpha into water? The specific rotation changes and finally reaches a value of 52.7 degree and stops. Similarly, you put beta D glucose in water. Its specific rotation starts changing and it stops at 52.9 degree. This change in specific rotation of optical active compounds with the time is called mutarotation. This is called mutarotation. Student, what we call this as mutarotation.
Yes, sir.
There is a change in specific rotation. Change in specific rotation, students. When you put alpha or beta form in water, and then after some time, what happens? The specific rotation becomes constant. Okay? So that means there is a conversion of one form into another. There is an equilibrium, students. And after the equilibrium is established, what will happen? The rotation will become a constant value, which is 52.7 degree. So we can say that alpha form, alpha D plus glucose, students, When you put in water, it is in equilibrium with beta D plus glucose, and after some time equilibrium is established and the specific rotation stops at which point? 52.7 degree. So now the rotation is not changing because equilibrium has been established between the two forms of the glucose. So this is the equilibrium mixture which exists. Okay? You have alpha beta form with small amount of open chain form, student. The specific rotation is 52.7 degree. This process is called mutarotation. But I try to say that you have alpha D plus glucopyranose. Then you have open chain structure or form of glucose. Okay? And then you have beta D plus glucopyranose. There is an equilibrium between these three, students, equilibrium between these three in water. When equilibrium is established, what happens? The alpha, the specific rotation value becomes 52.7 degree. How much it becomes? 52.7 degree. This process is called mutarotation, students. What do we call this as? Mutarotation. You have noted down, students? Noted everything?
Yes, sir.
Okay. So, students,
Yes, sir.
what we have been telling you, what I told you, students, the cyclic structure of glucose, Haworth structure of glucose, the structure of fructose, open structure of fructose, and then we also told you the cyclic Haworth structure of fructose. Fructose, we have shown you 5-membered ring. That's why the name is furan fructose. And the glucose, we have shown you 6-membered ring, students, pyranose ring. Then we have explained to you what are anomers. They differ at carbon 1 or carbon 1 of aldohexose, carbon 2 of ketohexose. They are differing in the configuration of that carbon at which hemiacetal or hemiketal is formed, students. Ketones will form hemiketal, aldehydes will form hemiacetal. In glucose, C1 carbon is the one where configuration is different. Therefore, alpha D plus glucopyranose and beta D glucopyranose are anomers. In fructose, since carbonic group is at carbon 2 position, it is forming a hemiketal with carbon 5 of OH group. So the anomers of fructose will be differing at OH group at carbon 2. And epimers are those stereoisomers which differ in the configuration of OH of any asymmetric carbon or any optical center, stereocentral carbon. So D-mannose and D-galactose are related with glucose in what relationship is their, student? They are epimers of glucose. D-mannose and D-galactose are epimers of glucose. Then we told you, you have alpha rotation, alpha form of D plus glucose, beta form of D. Their specific rotation is different. Polarimeter is used to measure their specific rotation. One is plus 19 degree, other you have seen is how much? How much did I write the value? See, so much difference is there. Is it plus 19 degree? Alpha is 112 degree. But when you put them in water, what happens? Specific rotation changes. And after some period of time, it becomes constant 52.9 degree, student. This is a change in specific
Sir, your
rotation.
voice is breaking again.
Anyway, we are going to stop the video only on few seconds. So what is happening in this case, student, there is a change in specific rotation with the time. This is called mutarotation, and therefore equilibrium is established between alpha and beta form of glucose. There is some open chain form of glucose also which exists in water solution,
Yes, sir.
and the specific rotation attains a constant value after some period of time. This process is called mutarotation. All right, students, we are stopping at this point. We will continue about polysaccharides and disaccharides in our next class. Okay, then we will meet you in our next class.
Good, sir. Okay.
Okay.
Thank you, sir.
Thank you. Okay.